1 over h bar AS, and then we have specific heat capacity here. So this is 1 over the resistance times C, 1 over tau LC. So we can write this as, we've got here TH over tau LC. So that's the particular part, and then we have the homogeneous part. Then the particular part, we have dTp, dt, plus Tp over tau LC is equal to our T infinity over tau LC. Let's actually write out the expression for T infinity, just so we have it in one place here. It's A0 plus A1T plus A2 T squared plus A3 T cubed, all of that over tau LC. Okay, so we have here our homogeneous solution, or homogeneous ODE. And then on the right-hand side, we have the remainder, which is the particular. So this, again, all has to equal 0. And this, we have to find a solution. Right? So this is our particular. We have to find a solution that satisfies that, and then add them back together. Questions on this so far? Okay. Okay, so then let's go to the next slide here. So now we've got our homogeneous equation and our particular equation. Let's go through these and solve them. So starting with the homogeneous, what can we do? So we can take this and say, look at this for a second. It's actually a separable equation. If I take this thing over to the right-hand side and then divide everything through by TH, and multiply everything by dt, we can get the th and the time separate. So let's do that. It ends up being dth over th is equal to minus dt over tau LC. Okay, we've separated that. So now I can integrate both sides. So I'll integrate the left hand. I'll integrate the right hand. That we end up with, on the left, we have log of th. On the right, we have minus t over tau LC plus some constant of integration. I guess we'll call that C1. All right, we're integrating. It turns out, right, you would have a constant of integration on the left as well, but just bring that over, bring your two unknown constants together, you just have one. So this is the temperature solution for this homogeneous side. Let's go through and actually solve fully for TH just to have an expression there. So we'll take each side, exponential of each side. So exponential of a log is the thing inside, which is TH. And then on the right-hand side, we have exponential of minus T over tau LC plus C. So remember how exponentials work. If you have exponential of two things added together, you can equivalently write that as exponential of the first thing times exponential of the second thing. Again, exponential of a constant is still just an unknown constant. We don't really care that we're taking the exponential. It's just an unknown constant. So we can then rewrite this as TH is equal to C1 exp minus T over tau LC. Right? Make sense? So this is our homogeneous solution, general solution for this problem. If you look at it, it should kind of make sense. You see that there's some constant you're starting with, C1, and then as time increases, the argument here gets more and more negative, meaning you're taking the exponential of a growing negative number. So what you should see is you start off pretty high, and it will sort of tail off. And that's the kind of response we expect for a transient problem. You expect an initial response that's pretty strong, and it'll tail off as the temperature approaches. And so this is always kind of this characteristic response you're going to see in a transient problem. Okay, so then let's look at the particular solution. On the particular solution, what do we have to do? We have to make a guess for TP that looks something like the right-hand side. Remember the rules, maybe it's a good reminder of what the rules are for guessing what the right-hand side should be, or guessing what TP should be based on the right-hand side. We have to look at the right-hand side and see, okay, I need some way for this set of operations to produce that. Therefore, I need to guess something for TP that looks like that, but it should be everything that's possibly over here and its derivative, all the way down until the point where you can't take, you get 0 for the derivatives. So that would be, to be specific here, I'm going to guess TP is equal to, I see a t cubed term over there, so I would need to guess some constant times t cubed. We've already used C1, so let's call this C2. And then I need to take a constant times every derivative of that, which could also be needed to produce that. So that's going to be just writing it all the way out. It would be what's C2. Let me do it this way, just to be consistent with my notes. Let me do it this way. So I'm going to write C2 plus C3t plus C4t squared plus C5t cubed. Right? That'll save me some mental mapping. But the idea is, right, we guess that original highest order term, and then we take the derivative all the way across and have constants. These are unknown constants. We don't know what these are. We have to now go through and figure out how to determine them based on the particular solution. So we go back now, we have to substitute our guess in to this expression. So we would see then the left-hand side, which is the differential of this, would be C2 goes away, so we have C3 plus 2 C4 t plus 3 C5 t squared plus this TP over tau lumped, which is this whole thing again, which is C2 plus C3t plus C4 t squared plus C5t cubed divided by tau LC. I guess I'm calling it tau lumped in the written notes, but I mean tau LC, by the way. So that's the left-hand side. That all has to equal the right-hand side, which is A0 plus A1t plus A2t squared plus A3t cubed over tau LC. Okay, so this is kind of messy. And at this point, you might be really confused about how we're going to solve for the constants. Right? We have, 4 unknown constants here. We don't have any extra boundary conditions. So what do we do? Well, it turns out, kind of like the idea of orthogonality, where everything, where all these different terms are providing unique information, you have to think about it like follows. So if you look at this equation, if I take the value of any value of time and plug it in, I have to somehow force the left-hand side to equal the right-hand side. Again, we know everything here. We know the values A0 through A3. We have those handy. We know everything here except for the time. I plug in a time, the left has to equal the right. Now, if I start varying time, what has to be true? Well, it can never be that the linear term somehow fully compensates for the value of the quadratic term or the cubic term. The linear term has to match the linear term in some way. The quadratic and the quadratic and the cubic and so on. So what you'd go through and do is say, okay, I'm going to find all the terms on the left that are first constant. So I see that there's a C3 over here. I see that there's a C2 over tau. I see on the right-hand side that there is an A0 over tau. So that gives me one equation, right? I can write out for the 0th power, t to the 0th power, I can write on an equation based on this, which is C3 plus C2 over tau LC has to equal A0 over tau LC. That's an equation. That has to be true in order for this expression to be valid for all time. It's a little bit tricky to think about, but you can convince yourself, right? The same thing, again, would be done for all the other terms that are present here. So let's write out some of these. Hopefully I don't run out of room. So T1, so that's t to the first power. That's going to give me 2c4 times t plus c3 times t over tau LC equals a1t over tau LC. T to the squared powers, similarly, 3c5t squared plus c4 t squared over tau LC has to equal a2 t squared over tau LC. I've run out of room, but I'll put it over here on the left. So t to the cubed power would be c5 t cubed over tau LC is equal to a3 t cubed over tau LC. Okay, so that's just sorting things and putting them in the right bin. Okay, so now you've gone through the homogeneous solution, right? You have your TH, you have your TP, you've guessed it looks like this. We now have 1, 2, 3, 4 equations that we can use to solve for the 4 unknown constants. So we now have a fully defined TP, right? Any questions on this? Okay. Okay, so then we go back and we can add these together on the next page. Let's see. So there's my ODE. Add them back together, and I get temperature is equal to C1 exponential minus T over tau LC plus C2 plus C3T plus C4T squared plus C5 T cubed. But I know I can solve for C2 through C5 using those expressions that we just wrote on the last slide. All right, so I know everything except now for C1. Right? I don't yet know C1. So how do we deal with that? Well, we have a transient problem. We have to enforce a boundary condition. What is our boundary condition for a transient problem? Yes. Initial condition. By the way, we'll get to an example. It doesn't have to be the initial condition. You just need to know a condition of temperature of this body at a particular time. Right? That's all you need. Often it's given to you as an initial condition problem. So, okay, so we say our initial condition was T at time equals 0 is equal to the initial temperature, T initial, which just means we plug it in, and that becomes T at time equals 0 equals T initial equals C1 exponential time, so minus 0 over tau LC plus C2 plus C3 0 plus C4 0 squared plus C5 0 cubed. Exponential of 0 is 1. So you end up with this saying T initial is equal to C1 plus C2. Everything else goes away. Again, we know, right, we already know C2 from the previous expressions. So this lets us solve and say, yeah, C1 is equal to T initial minus C2. All right, and we're done then. Now we have our full solution. All right. Last time we went through this point, we got to the point of calculating the BO number here, which is the ratio of resistances. Now I've gone in and calculated this time constant, the tau LC. So if we just evaluate this, let's look at what that is. So tau LC, 0.28 seconds or 0.29 seconds. It's hard to see. But okay, this tells us that, yeah, we didn't waste our time by doing that derivation. We're going to see a response that's interesting. That's not just a trivial outcome. Okay, so that was step 2 in the process. Here's our solution. These are the equations that we derived for the particular solution. So you don't necessarily have to solve explicitly for these, or you can just plug them in. If you're doing this in Python, you would. But it wouldn't be too hard, right? You're just solving a system of equations. So that gives us C2 through C5. Then we apply our boundary condition here to get the initial condition, the value of C1. And then this is the solution that we identified here. So temperature, C1, exponential, and then the evaluation of the particular solution. Right? And this is at any moment in time. One thing I'll caution you on, if you're using e's to solve this stuff, don't call time lowercase t and temperature uppercase t, because e's doesn't differentiate between upper and lowercase. So you want to use like a different variable for that. Okay, so we plug this in. Here's our expression of t infinity, by the way. And we can hopefully solve, and we see that, well, at time 0, t is equal to t initial, so that's not that interesting. What we want to do is maybe plug in different values of time and see the response. So I've got a parametric table here. What I've put in is time from what? Up to 0.5 seconds, so 0 to 0.5 seconds. And running this table, we're going to evaluate both T infinity and the body temperature. You've already done that. And then you can plot it. I think actually I need to generate a new plot. So time, T infinity and T. Oops, T infinity and T. And let's do it this way. So here's the response of the T infinity function. And then here's the response of the body. Right? So you can kind of see it's doing some interesting stuff there. It's responding. It's the time constant's 0.3 seconds, so it's not quite able to get up to the peak of the ambient temperature. But it is, it's making progress. It's doing something interesting. Right? So that's how you would implement this analytical solution in ease. It's pretty straightforward. Questions on that part of it? No questions? Okay. So let's go back to the notes then.